got it. Sharpness. So one thing is that what you would like to say is, define dq as this threshold in D, so that exactly as Tom said in the last talk, that there's a sharp threshold. So if D is at least dq times 1 plus epsilon, with high probability you're not colorable. If D is less than 1 minus epsilon times dq, with high probability you're recolorable. It turns out we don't even know that such a D exists, a dq exists. What we do know is from Freedgut, and this is similar to the telegram theorem Tom mentioned, this is a general purpose theorem for proving sharp thresholds. And what Freedgut gives is that there is some sequence dq of n so that you're sharp around this sequence. But for all we know, it could oscillate like this. So that's still open, whether there's an actual dq that doesn't depend on n. Good. So yeah, it's open to show that dq can be taken independent of n. Now, here's the physics prediction. And the physics prediction is based on the cavity method. I'll keep it vague for now, but at the very end of the talk, I'll give you a baby version of the cavity method and hope that gives you some intuition. But the main paper is this paper by Shorkala, Montanari, Ricci Terzingi, Semerjan, and Zdeborova in 2007. And this is just an amazing paper, and they basically use this cavity method to predict all sorts of phase transitions for all sorts of random constraint satisfaction problems, including random graph coloring, including random k-sat. But one way to start understanding what they're thinking is that instead of thinking about when there's a coloring or not, what they are really trying to understand is the probability distribution over, say, uniform proper Q colorings of a graph. They want to understand what are the sort of properties, correlation decay properties, and things like this of this probability distribution. And even going further, they're not actually going to be looking at Q colorings. What they'll look at is some positive temperature version of this. So, and we'll get to this in this talk, the anti-ferromagnetic Potts model. Because of course, once there's no colorings, you can't talk about the uniform distribution, but you can always talk about the Potts model. Okay, so I'm gonna sort of describe what this picture is suggesting. So this is, how many of you have seen this picture for random constraint satisfaction problems? So some people. I want to describe it to people who haven't seen it, but then also give a big caveat that will set up David Gamarnik's talk tomorrow. And so what is this picture? It's a cartoon picture of the set of all proper Q colorings of your random graph as the edge density increases on the x-axis. Okay, and these are threshold or phase transitions that were predicted by these physicists. And the idea is for very small d, basically all the proper Q colorings exist in one big connected component. So you can get between two proper Q colorings by just changing one color at a time and staying proper. After this clustering or shattering threshold, the state space breaks apart into exponentially many clusters, each of which have exponentially many proper colorings, and you actually can't get between two different clusters without violating a bunch of edges. But they all look roughly the same size. The important threshold for today's talk will be the next one, the condensation threshold. And it's at this point where a constant number of clusters actually make up almost all the colorings. So there you have a constant number, a random number of dominant clusters, and everything else is very, very small. And then, of course, there's the satisfiability threshold or the colorability threshold, where this set is empty. Okay, so yeah, so they predict these different phase transitions. My caveat, and I think this is important to know now that we know a bit more, is that this is really an equilibrium picture. This is talking about what do almost all solutions in the state space look like. And it completely neglects, say, you could have some exponentially small fraction of solutions that are doing something that looks completely different than this picture. And so you have to be very careful about associating to this picture anything about algorithms. And somehow when you maybe when you've seen this picture before, you were told that they're like somehow these thresholds mark hard places for algorithms. That's really not true. And what we know is that somehow for some models, there are exponentially small fraction of solutions that actually all efficient algorithms that we know find these rare solutions, and it has nothing to do with the picture. Okay, but what David Gamarnik will talk about in the next couple of days will be something much stronger, which he's going to talk about all pairs of solutions or all tuples of solutions, which is very different than this. The shattering threshold coincides roughly with the known algorithmic threshold, but there's no result saying that the shattering threshold implies hardness of algorithms. Yeah, and we have models where you have like freezing of all solutions and still have efficient algorithms. Yeah, so this is my caveat. Okay, good. So let's talk more about the condensation threshold, and this is what we're gonna talk about through the talk. There's a few different ways to define the condensation threshold. You know, one I gave you in a picture, but here's a more mathematical way to define it. What I'm looking at is this limit, and I'm taking the nth root of the number of proper colorings. This is a random variable. I'm not taking log and dividing by n because you don't want to take log of 0. But I'm taking the nth root and taking a limit. And the question is, does this equal the limit of the nth root of the expectation? So this is like what I talked about yesterday about whether you can switch the log and the expectation. Okay. And one way to define the condensation threshold is it's the largest d, the sup over d, so that these things are equal. Okay. So first exercise for you all, I claim that this is at least 1. Okay. This goes back to Tom's talk, right? What happens below 1 about the components? They're disconnected, they're small, they actually are basically all trees. Okay, there might be some small components, but you can actually calculate for any tree, you can calculate exactly the number of Q colorings, and it doesn't depend on the tree structure. So if you realize that and realize all components are trees, you'll see that actually you get this this equality in the limit below the giant component threshold. And of course, the condensation threshold is a lower bound to the coloring threshold. Because if this holds, definitely it's not 0 with hyperbole. Yeah. Yeah, that's a good question. Yeah, let's take a limb soup. You're right. This is important to distinguish. Yeah. Yeah. It turns out they're the same. Yeah. This is true. Okay, so the question is, can this, and you can think of this, you know, this is like the first non-analytic point of the free energy, as I described it yesterday. So the condensation threshold, in that sense, is the first phase transition in this model on the level of free energy. And the question is, can we determine the condensation threshold for this model? And there's a couple different approaches. So one approach is to try a intricate, sophisticated version of the second moment method. So the second moment method, it fails at some point. It doesn't always work, but there's a couple things you can do. One is you can change the random variable. So instead of asking for, you know, what's the random variable is the number of proper colorings, you can change the random variable. You can look for proper colorings with some special form. You can look at things that sort of can be extended to proper colorings. You can look at a different random variable. The other thing you can do is you can condition on typical properties of the instance. And so it might be that like when your degrees, say, are very unbalanced, this contributes a lot to the second moment of the number of colorings and helps it blow up. But that doesn't happen with hyperbole, so condition on the hyperbole event that your degree sequence is nice. And then do the second moment from there. So this is the approach, say, by Ding, Sly, and Sun when they proved their result for random KSAT. There is a result by Baps, Koja-Oglin, Hederich, Rossman, and Velenik that determines the condensation threshold for random graph coloring for large Q using this. And the Dingsley and Sun result also is for very large K that you need to carry through these calculations. But I want to talk about a different approach, which sort of gives you a little bit more intuition for the cavity method. And this is a paper from a few years ago with Koja-Oglin, Sharkala, and Zdeborova. And what we're going to do is identify the condensation threshold for all Q, so not just large Q, by carrying out calculations from the cavity method rigorously. Okay, and that's the idea. But to do so, we actually won't be carrying out the cavity method in this model. We're going to be carrying out the cavity method in a different model. And that model is itself kind of an interesting model. And so that's the stochastic block model. And what is this model? It's a toy model of an algorithmic problem called graph partitioning. So you have some graph and you want to partition your vertex set either into very well-connected blobs or very not well-connected blobs. And this is, you could argue that this is some basic data science model or problem, but the toy model is very nice mathematically, and it comes up in a lot of places. And so what's the model? You start by having a set of n vertices, n is large. You divide them randomly into Q parts. And here I'll always be thinking of Q as a constant. Like if you like to think of Q as 3, that's perfectly fine. So divide it into Q parts at random. So they'll roughly be the same size. And then you put random edges into your graph, but with the probability is different whether if the edge is within a part or crossing a part. And so let's say A over N if you're within a part and B over N if you're crossing a part. And here we're thinking Q, A, and B are all constants, and N is getting big. And of course, if we just took A to equal B, then we would have the Erdős-Rényi random graph. So we're going to think A is not B. So you get some graph that looks like this. But of course, you don't know the red edges and the blue edges. And we're going to present to some algorithm or to some person the adjacency matrix of this graph, but of course, not tell them what the partition is. Okay. And then the algorithmic problem is to recover as best you can what the partition was. And now I've written all these caveats, but when I say recover, of course, there's like, you can label the parts 1, 2, 3, 4, 5, but recovering means up to the best way to permute, because of course there's no difference in the labels. Okay, so that's the algorithmic problem. Can you recover the original partition just seeing the graph? And there's a couple different notions of recovery. One would be exact recovery up to this permutation. And this is actually going to be impossible in this regime because we're in a sparse regime. Actually, we'll have a constant number of isolated vertices. So there's no way to know which part these isolated vertices belong to. Instead, we're going to be asking for something much weaker, nicely called weak recovery, which is for some fixed epsilon bigger than 0, find some partition that agrees after this permutation with the original partition, the truth, on at least 1 over Q plus epsilon fraction of vertices. So it's very easy to get 1 over Q. You just randomly answer. And so this is saying just do a tiny bit better than random. And that's weak recovery. And we want really to succeed with, let's say, probably tending to 1 as n goes to infinity. Okay, any questions about the model? So this is like the statistical inference of the title. You are presented, you have this ground truth, which is the partition. You're presented some noisy data that respects the ground truth, the edges of this graph, and now you're supposed to recover as best you can the ground truth from the noisy data. Okay, so 2 main questions. One, is weak recovery possible? And second, can we achieve weak recovery with an efficient algorithm? So one, say, running in polynomial time and n. And again, there's beautiful predictions from statistical physicists. And this is Dessel, Sharkala, Moore, and Zdeborova from 2011. This paper really kicked off a ton of work in mathematics and computer science on this problem because the predictions were so nice. And so what they predicted was there's actually two thresholds, and sharp thresholds in the sense of free gut. The information theoretic threshold. So there's some threshold where below this threshold, there's no way to achieve weak recovery. Okay? It's impossible, no matter how much time you spend. But above this threshold, there is an algorithm, although it might take a long time. And then the algorithmic threshold, their prediction was below this threshold, there's no polynomial time weak recovery algorithm. And above this threshold, there is an efficient algorithm. Okay, so two thresholds. Yeah, so I didn't quite say, but like you can think of fixing the ratio of A to B and then letting the constant in front go up. So it'd be a constant of that. I'll get to that scaling in a bit, but I'll say it precisely here, at least for Q is 2. And so for Q is 2, actually, they conjectured that both thresholds occur at the same point. And so here the threshold is A minus B squared over 2 equals A plus B. So you can see now that somehow it's saying that for a given difference, the sum should be large. And then for Q is 3, they also predicted the threshold should coincide. Q is 4, it depends a little bit on the parameters, whether they predicted it to coincide or not. But for Q is at least 5, they conjecture that the two thresholds always are different. There's a gap. Okay, so and this is what we now call a statistical computational gap, where some statistical inference problem is solvable with, say, exponential time, but not solvable, we think, in polynomial time. And, okay, this is interesting, I think, just as a statistical question, but it's also, from a computational point of view, this is exactly the kind of very interesting problems we're looking for. Candidate hard instances for NP hard problems. And here, they're making these beautiful predictions about the existence of hard computational problems in some specified range of parameters in this very nice random graph model. So those are the predictions. So what is known? For Q equals 2, that these thresholds coincide for the two-part model. This was proved by Mosul, Niemann, and Sly, and Masoulier. And then for all Q, Abe and Sandon proved the existence of efficient algorithms above the conjectured algorithmic threshold. And this is something called the Kestem-Stigum bound. So it has a nice form. Okay, so what does that leave open? Well, one thing it leaves open, and this is a challenging problem, is prove some kind of hardness below the conjectured algorithmic threshold. Of course, proving that that conjecture that there's no polynomial time algorithm, that's harder than proving P not equal to NP. So we don't really expect a full resolution of that anytime soon. But as you'll see in David's talks in the next couple of days, there's different types of evidence you could give for algorithmic hardness, but we still don't have a really convincing understanding for this problem below the algorithmic threshold. Yeah.
Something that you would probably be satisfied with reducing the state. Like the existence of a good algorithm that applies.
Yes, great question. So if you didn't hear, one convincing piece of evidence would be saying reducing this problem to P versus NP. That's an enormous open problem, reducing average case complexity to an assumption like that. We don't know how to do that for any of these problems, but that's that would be like the holy grail. Yeah. Yes. Yeah, so there is some evidence of that. Yeah, who's that by the way? Okay. Yeah. Yeah, so there is some version of hardness, some class of algorithms that we know can't succeed there. Oh, did you establish it is equal? Ah, good. Okay. Yeah. Oh, good. Okay, very good. For large enough degree. Okay. Okay. So still there's something open for 3. Okay. Okay, but good. Thank you. Good. So that's sort of the landscape there. And there's very nice surveys about this whole model by Abe, and Moore also has one. Really interesting thing with lots of nice connections. But the other thing is establishing the information theoretic threshold. Okay, so that's also open, at least for Q at least 5 or Q at least 4. And so that's what we do in this paper. We establish the information theoretic threshold, but in the disassortative case. So only in the case that B is bigger than A. So somehow in the less natural case that you're looking for clusters that are not well connected with the strong connections between them. Although there is a special case that is more natural. If you take A to be 0, so what happens if you take A to be 0? You're picking this partition of into Q parts of your vertices, and then you're only adding edges that cross the partition. You're what we call planting a coloring. This original partition is guaranteed to be a proper coloring in your graph, and then you can study this random graph model, but where you actually know that you have at least one proper coloring. So that's the planted coloring model. And that's this extreme case of the stochastic block model. Okay, so what is the answer? So no, not known for A0. Yeah, somehow that's not a simpler case. Yeah. So I've given you two theorems, right? Sort of. I said we determined the condensation threshold for all Q, and we determined this information theoretic threshold in the stochastic block model. But what is the answer? What is this threshold? Depending on your taste, you may or may not be satisfied with the answer. But first, what we're going to do is we're going to frame both problems in terms of the anti-ferromagnetic Potts model. So let me just define that. So it's like the Ising model I defined yesterday, except you have Q colors, assigning Q colors to the vertices of the graph. The partition function you sum over all colorings, exponential of minus beta times the sum over edges indicator you get the same color. So we're penalizing exponentially in beta, having monochromatic edges. Okay, so now if you imagine you take beta to infinity, this is the uniform distribution on proper coloring. Okay, but it's a positive temperature model. All configurations when beta is finite have positive probability. And what we want to understand is what is this free energy? So limit of 1 over n expectation log z. And Q will always be fixed. Okay, so I didn't even want to write this myself, so I copied it from the paper. But let me walk you through this, because this actually is going to tell you what the cavity method is doing. Okay, so I have here a function called beta Potts Q of Q, D, and C. So Q is the number of colors, D is the average degree in this Erdős-Rényi random graph. C is something that is just a function of beta. So C is really just 1 minus e to the minus beta. Okay? And what is this? This is an optimization problem. It's a soup over pi in this curly p squared star of Q. I'll tell you what that is in a second, of some expectation. And so let me just work through the objects. So P of Q, so Q in brackets just means the integers 1 up to Q, so the set of colors. P of Q is a set of all probability measures on colors. So you can think of these as marginals. Like one possible probability measure is just the uniform distribution on Q colors. Another would give like 50% to red and 10% to blue, 10% to green. Okay, all of these are probability measures on Q. So that's P of Q. P squared of Q is the set of probability measures on Q. Okay, so you can take, a random marginal. Okay, and P square star of Q is the subset of these ones whose expectation is the uniform measure on Q. Okay, so that's what we're optimizing over. It doesn't sound like a very nice optimization problem, I'll say, but we're optimizing over this. And what do we have? We have two terms. We have something plus and then something minus. And it's an expectation in terms of a few random variables. One is a gamma. Gamma is, maybe I wrote it on the next page, but gamma that appears here and here, this is just Poisson D. Okay? So that's kind of nice, Poisson D. And then you have like a bunch of mu I pi's. These mu I pi's are independent samples from pi. So remember, pi is a distribution on marginals. So these are random marginals. And I have some expectation involving some function of, okay, this is kind of interesting. You multiply over Poisson D functions with these marginals. And the other one, keep in mind, we have minus D over 2 times something where you're multiplying together something involving 2 marginals. That's as much as you sort of need to take from this formula. But that's some optimization problem. And the theorem is that the condensation threshold is in this Potts model. So now we're fixing D and looking at condensation in beta, is the largest beta so that the optimization, this thing is, or the smallest beta so that this thing is bigger than sort of the expectation, the annealed free energy. And the theorem says if you're below this condensation threshold, then the free energy is the annealed one. It's 1 over n log of the expectation, and false otherwise. Okay, so that's the condensation threshold in the Potts model, but it's given by this solution to this kind of nasty optimization problem. Okay, and the point is that this same optimization problem is going to characterize both the random graph coloring condensation threshold and the information theoretic threshold. So here's the theorem for the random graph coloring. The condensation threshold is given by the smallest d, so that when you solve this problem, you get something bigger than the annealed free energy. And the theorem, what does it say? It says that you converge in probability. The 1 over n log number of colors converges in probability to the 1 over n expected number of colorings. And then if you go above the condensation threshold, you're exponentially smaller with high probability. Okay. So this is the condensation phase transition. Now the stochastic block model results. So here's the parameterization I mentioned. So you take A and B both to be proportional to these things. So it's D out front, and then Q times e to the minus beta inside, and just Q on the top. So we're the ratio between A and B is e to the minus beta. And what it says is the information theoretic threshold, again, is the smallest d, so that the solution to this crazy optimization problem is bigger than the annealed free energy. And yeah, and so really, exactly the point at which this optimization problem changes behavior marks the random graph coloring condensation threshold, the Potts model condensation threshold, and the information theoretic phase transition in this model. And let me just say that the other way to interpret that the annealed free energy is just by plugging in for pi the point mass on the uniform distribution. So that's a possible solution. With probability 1, you pick uniform marginals, and that's the value you would get from the functional there. Okay, so that's the result and sort of the flavor of the predictions of cavity method. Now, when the statistical physicists write a paper, what they do is they have this formula, and then they actually try to solve this optimization problem for given values of D and Q, and that's how they come up with precise predictions of what's happening at, like, Q is 3, Q is 2, but actually it's quite hard to solve those problems in general. Okay, so I want to just give an outline of the proof to see where does this cavity method come in. And so our idea is to carry through the replica symmetric cavity method. I'll explain what that means, to compute the free energy, this limit 1 over n. Actually, I should reverse log. No, that's right. Expectation log, but not in the random graph, not in the Erdős-Rényi random graph. We're going to do it in the graph that is the stochastic block model. Okay, but look at the Potts model partition function on this random graph. Okay. And then we're going to show when the solution to this optimization problem, or the optimizer, is the point mass on the uniform distribution, the stochastic block model and the random graph are close, meaning like little o n KL divergence. Okay, so how do we do this? There's some key ingredients. One is something called the Nishimori property. But what that's saying is I can give you a graph and say that this came from the stochastic block model. It was generated by planting a partition, then generating the graph. And if I give you the graph, you can figure out what is the posterior distribution on the planted partition. It turns out that it is exactly the Potts model, the antiferromagnetic Potts model on this graph with the same beta. Okay. So somehow a sample from the Potts model is a sample from the posterior distribution. That will come in useful. Another extremely useful tool is something we call a pinning lemma. And this goes back to Montanari and Raghavendra and Tan. But actually, if you haven't seen this, this is kind of a cool fact about probability theory. So I want to fix Q, which is like my number of colors. I want to fix, you can choose some large t, you can choose some small epsilon, and there's some L that exists that is just a function of Q, T, and epsilon. And so that the following holds for every n and for every probability distribution on Q to the n. Okay, so this is just a fact about any probability distribution. It doesn't have to be a Gibbs measure, Potts model, or anything, but the following holds. I'm going to construct a random measure in a certain way, and then it's going to have a really nice property. So how do I construct my random measure? I pick some random coordinates, call them S, in my 1 up to n, by picking like this integer uniformly between 0 and L, this big number, big constant number. And I'm going to pick one sample from my probability measure mu. And then what I'm going to do is say mu hat is the conditional measure of mu, where I condition on the coordinates in S get the value given by this one sample. So I'm going to pin their values to the sample, but just a constant number of coordinates. And this thing, remember, n can be anything. So think of n as being millions and billions, and I'm pinning 100 coordinates. And then with probably 1 minus epsilon, so 99% chance, mu hat has the following property. If I average over all t tuples of coordinates, the total variation distance between the joint distribution on these t coordinates and the product distribution with the right marginals, that's small. So this is like some extremely weak but very general correlation decay property. It says like if you average over all tuples of the graph, you don't have correlation. Okay. But that's true for any probability measure, which is kind of cool. Okay, so that's one thing. And then the way we'll actually carry things out is something called the Eisenman-Sims star scheme. And this is a way to couple a random graph on n vertices with a random graph on n plus 1 vertices and compute the expected change in the log partition function between the two. And then something I won't even mention now is that this Eisenman-Sims star scheme will give us one side of the bound, and the other side is due to something called the interpolation method that goes back to Guerra for the SK model. And this is somehow a little bit magic when it works. And this is basically the reason we can't do it for a sortative stochastic block model. This ingredient just doesn't work. And this is a huge open problem in the area to somehow get around the cases where interpolation method doesn't work. Okay, so let me use the last 5 minutes to give you a toy version of the cavity calculation and the Eisenman-Sims star scheme, because this at least should explain in that formula, why did we have those two terms? Why did we have some product over some random marginals and Poisson D and everything like this? Okay, and at the moment, I'm just going to imagine that we're trying to do this calculation in the random graph instead of the stochastic block model graph where, you know, the edges actually are added with some probabilities that depend on the planted spin. Okay, so you know, if you've studied random graphs, you can try to come up with this yourself. How would you couple a random graph, a sparse random graph on n vertices with a random graph on n plus 1 vertices? Okay, so Gn is my Erdős-Rényi random graph on n vertices. Gn plus 1 has one more vertex. Well, I have to add the vertex, of course. Well, how many neighbors is it going to have? Well, it's going to have binomial n-1 d over n, which is essentially Poisson d. And well, there actually could be any one of the neighbors, any one of the vertices before. So what I'm going to do is I'm going to add that new vertex and join it to Poisson d uniformly random neighbors in the existing graph. Okay, those are the red connections. And you might want to stop there, but you did something wrong if you stop there. I just added Poisson d edges, but that means I have sort of d over 2 in expectation too many edges. And so, the edge density in the old part of the graph is a tiny bit too high. And so I should remove some edges. And so I should remove, let's say, Poisson d over 2 edges from the rest of the graph. Just so I don't start accumulating too many edges if I keep doing this. Okay, so now the interesting thing is that the change in the log partition function, and this is a property of Markov random fields, and the reason they're so useful to work with, the change in the log partition function, or the partition function, when you go from gn to gn plus 1, only depends on the joint marginal of these purple vertices, all these connection points. The rest of the graph doesn't matter. The change in the partition function only depends on their joint distribution. Okay, so if we knew, let's say, that their joint distribution factorized, if they somehow the marginals were independent, or the spins were independent at these points, well, then this change in partition function would have a especially nice form, right? Because now we're just writing things in terms of some independent random variable. Okay. Now it's a little bit strange because you're picking random edges to remove, and that's kind of not nice. So what I'm going to do the coupling a little bit different. I'm going to start from this graph G0 that has a few too few edges, and I'm going to make Gn by adding Poisson d over 2 edges, and I'm going to make Gn plus 1 by doing the connection. Okay. So then really I can say that these can, and then of course the change in log partition function is just the sum or subtraction, however you like, of these two changes. And each of these just depend on the joint distribution of these connection points. And the key thing here is these connection points, once I do it this way, are chosen uniformly at random from the graph. They're chosen in IID fashion from the graph. And well, and we want them to be basically independent, but this is exactly this type of extremely weak correlation decay you get from this pinning lemma. That if you randomly pick t vertices from your graph, then with high probability, the total variation distance is close between the joint distribution and product distribution is small. So it's extremely weak notion of correlation decay, but it is exactly what you need in this one step of this Eisenman-Stem star calculation. And so if you knew that they factorized, then you could get an expression for the expected change in the log partition function just in terms of the distribution of marginals. So what do I mean by that? The distribution of marginals means pick a random vertex in G0 and look at its marginal. That is a probability measure in this set p squared, right? Because you're picking a random vertex and saying what's its marginal. That's a measure in p squared. And so then you can see that this expected change in the log partition function is a functional on measures in this p squared. And so that's how to do it. But we need to apply the pinning lemma, right? And so how do we have access, or how do we control what a sample from mu G0 is? Okay. And in general, actually, you can't really do this. So if you tried to do this just for the Erdős-Rényi random graph model, it wouldn't work. But the Nishimori property says that actually we can, in distribution, like the original planted coloring is a sample from the Gibbs measure. And so we can just pin to the original planted coloring. And that we can keep constant as we do this again and again and again, which is the key. And so somehow it all works together nicely here. So let me conclude. So I sort of walked you through a high level about how you can actually apply the cavity method to this planted antiferromagnetic Potts model, which is like the disassortative SBM, and actually make this calculation work. Now, it did rely on some special properties of the model. For one, we had to carry through the interpolation, but also what it relied on was like this fact about this trees in the random graph that I said, that at very small d, these things were equal. And that's not true for lots of models. For like random k-sat, that's false. And so it required some sort of special symmetry, and we don't know how to get over that. Because what you would really like to do is you would like to carry through the same framework of applying the replica symmetric cavity method to some planted model in somehow some higher order models. And so Young-Tak will talk tomorrow about what one RSB means. But a very high level, and if you can read this in like the Mizard-Montanari book, is that the one RSB picture is like the replica symmetric picture, or the replica symmetric method, except where you replace spins by marginals. So it's a spin model where spins are, instead of colors, they're marginals on colors. And so if you had a general purpose way and got over these things that we don't know how to do yet, you could, in theory, really carry through all the levels of the cavity method in this sort of planting and pinning way. But let me conclude there.